Welcome back. I thought that this screencast would be good to do a few extra examples on how parametric curves are graphed for the benefit of those folks who might want a few extra practices. So let's sketch. Let's sketch the parametric curve with the equations x equals t squared minus 4t plus 4 and y equals 2t plus 1 for t between 0 and 4. Let's graph that. So we'll take some time. We'll decide what the x and y coordinates are at those values of t, and then we'll graph and see what happens. Well, the t values go from 0 to 4. Plugging in those values to this generates certain x values. And 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, and so on, generates the y values. And so we end up with 4, 1, 1, 3, 0, 5, 1, 7, 4, 9. The curve looks like this with that orientation. Initial point here at 4, 1, terminal point here at 4, 9. It again looks like a parabola, which makes sense because if y is 2t plus 1, then t is y minus 1 over 2. And substituting this t here, x is y minus 1 over 2 squared minus 4 times y minus 1 over 2 plus 4, and that is definitely a sideways parabola because it's an x equals y squared kind of a curve. Parametric equations allow us to graph things that are not functions with relative ease. We didn't have any problem graphing this function, and that's kind of the point. All right, example 4. Let's sketch. X is going to be 5 cosine t, and y is going to be 2 sine t for t on 0 to 2 pi. Well, this time I'll use the machine. We used the machine to graph 6 cosine t and 6 sine t, but what if we change the 6 to a 5 and a 5 to a 2? Well, what in the world is that? Well, that thing looks like an ellipse. That thing looks like an ellipse. It looks like the distance from the center to the furthest x value is 5, and it looks like the distance from the center to the furthest y value up is 2. So it appears that the 5 and the 2 determine the lengths of the semi-major and semi-minor axes. But it's an ellipse, and it's centered at the origin, and we know how to draw it with the technology. Let's do a screen capture. Maybe we can do that. I can. Just to copy it where you are. Oh, too big. Too big. Great, and this will be the thing that gets picked as the background image for our video. Right, there it is. There it is. Just to be curious, what if we did something crazy? Oh my. What did the +1 do? Well, the +1 moved all the x's to the right 1, made them 1 greater. And this +2 made all the y's 2 greater. So the ellipse has the same shape. Lengths of the semi-major and semi-minor axes are as they were, but the center shifted to the point 1, 2. All right. All right. One more, just for fun. Just for fun. Let's sketch x equals 3 times t minus sine t, and y equals 3 times 1 minus cosine t for t between 0 and 6 pi. Let's try that. When you graph it on your calculator, you might want the x's to go from 0 to 18 pi, and you may want the y's to go from 0 to 6. You may find that that helps you to see the picture. I will do the same thing that you are doing. And that's why I asked us to change the window. It helps if you're looking at 0 to 18 pi horizontally and 0 to 6 vertically. Now my t values only ranged from 0 to 2 pi, but everybody has window settings, and your window settings, you can change that in the Inspire. In the Inspire, you can do it right there. You can change and get from 0 to 6 pi. This graph is what we call a cycloid. This is a cycloid. The cycloid is the graph that you get, is the shape that you get if you were to take some sort of fluorescent sticker and stick it on your bicycle tire and then ride the bicycle down the street. You would get a cycloid. The cycloid solves two famous problems of physics. It solves the brachistochrone problem and the tautochrone problem. The brachistochrone problem, if you were to set up a ramp as an inverted cycloid, just turn this thing upside down. If you were to set up a ramp in that shape and put a marble at the top, it would get to the bottom in the shortest time. That's the brachistochrone problem. It also solves the tautochrone problem. If you put two marbles anywhere along the ramp and let them go, they would hit the bottom at the same time. There are excellent museum exhibits, most notably in the Boston Children's Museum, set up around cycloids. So by the end of this lesson, you should be able to plot a few points of a parametric curve on your own, and also use your calculator to make a parametric curve appear. That's the goal. That's what you want to make sure you can do. And I hope that these videos have been helpful in that regard.